everyone. So today our focus is going to be on slides 39 through 49, and specifically those slides are going to be over redox reactions and then also displacement reactions, or those single replacement reactions. So first we want to go over redox. Before I start these slides though on redox, I just want to remind everybody that if you want to come on Saturday to Starbucks in Deerfield Town Center, then I will be there at noon to kind of like help answer any questions that you may have, or like just to study with you for your Chapter 4 test, which will be on Monday. So I will be there at noon. If no one shows up at noon, I'll probably wait like 15 minutes and then I'll probably just go. So if you want to study, then make sure you're there by noon, okay? Now let's go ahead and get started on redox reactions. So oxidation reduction reactions. In redox reactions, all redox reactions are about this electron transfer. So I'm transferring electrons in redox reactions. I kind of want to also compare a redox reaction to a neutralization reaction, okay? Now, in a neutralization reaction, we have acids and bases forming salt and water. Specifically, what's happening in an acid and base reaction is that the hydrogen ion is being donated from the acid and it's being accepted by the base. Now, these are very similar to redox reactions in the sense that in a redox reaction, we're transferring electrons. In acid-base reactions or neutralization reactions, we are transferring protons, in a sense, or we're transferring that hydrogen ion. We're moving that hydrogen ion somewhere. And in redox reactions, we're moving electrons somewhere. Okay, so the most common type of redox reaction is some type of corrosion. So anytime I hear about a corrosive reaction or corrosion, then I automatically should think that this is a redox reaction. Because when a metal corrodes, each metal atom is going to lose electrons, so it's going to form cations, and then that's going to combine with an anion to form some type of ionic compound. Now we have to remember, what does oxidation mean and what does reduction mean? So in this specific case, let's just look here. We have calcium metal is reacting with oxygen gas. So I just had some pieces of calcium out in the air, and it's reacting then with the air. Specifically, it's reacting with oxygen in the air. And because it's reacting with this oxygen, it produced calcium oxide. So I have these little calcium pieces of metal here. It's reacting with oxygen in the air. And because it's reacting with that oxygen, it's producing calcium oxide. So calcium is being oxidized. Oxidation occurs when an atom or ion loses electrons. So oxidation happens when an atom or ion loses electrons. I think we came up with a few different things last year. So there was oil rig, and then there was also Leo the lion goes grrr. So oxidation is when we're losing electrons, and reduction is when an atom or ion gains electrons. So let's go through. Okay, so we had oil rig was a way to remember oxidation and reduction. So we have oxidation is loss. In oxidation, we're losing electrons. And then reduction is gain. So that's one way we can remember. Or we can remember Leo the lion goes grrr. So a loss of electrons is oxidation, or a gain of electrons is reduction. And I think I like this one more because it actually uses the word electrons, and that's what redox reactions are all about. So I actually really like this one, but if you like this one, that's totally fine. Whichever one works. So oxidation is loss of electrons, reduction is gain, or Leo the lion goes grr, loss electrons, oxidation, gain electrons, reduction. Okay, so again, oxidation, we're losing electrons, reduction, we are gaining electrons. Why do we call oxidation oxidation? Why do we say that that's the loss of electrons? We call oxidation oxidation because it was first studied with reactions that dealt with oxygen. Many oxidation reactions occur because of oxygen from the air reacting with something then in the surroundings. So, and typically we're producing from that a metal oxide, and that's exactly what's happening in this case. I had some calcium pieces of metal that were here. This calcium was reacting in the air. Specifically, it was reacting with oxygen in the air. And because of that, it produced a metal oxide, calcium oxide. So calcium, in this case, is oxidized, and oxygen is reduced. And how do I know what's losing electrons and what's gaining electrons? So let's look at this. Guys, the reason that I'm pausing so much is because there's like a really huge bug that's like flying around the Promethean board. I'm not really sure what it is, so if I spaz out for a second, just don't really think anything of it. Okay. So I have calcium is reacting with oxygen gas from the air, and that produced calcium oxide. Okay, so this is calcium element all on its own. We haven't done these rules yet, but for those of you that were, for those of you who did not have me stick with me for a minute from last year, for those of you that did, hopefully we're going to go back over these oxidation rules, but let's go through this really quick right now. Any element that's all by itself. So I have calcium here. I don't see an ion. I don't see a charge with it. So this must just have a charge of 0, must just be neutral. Any diatomic molecule, any diatomic element is considered also to be neutral, so it has a charge of 0 here. But now calcium and oxygen are in an ionic compound, meaning that they are ions that have some type of coulombic attraction to them, so that attraction between those opposite charges is what's keeping them together. We know that calcium specifically has a charge of 2, plus 2, and oxygen specifically has a charge of minus 2. Okay, well, calcium went from having a charge of 0 to having a charge of plus 2, a positive 2. It became more positive. So did calcium gain electrons, which are negative, or did calcium lose electrons? Calcium must have lost electrons. And that's because it went from 0 to plus 2. If it gained electrons, it would have become more negative. So because it became more positive, it must have lost electrons. And we know, according to our Leo the lion goes grr, if I lose electrons, that must be oxidation. Okay, well, if calcium lost electrons, oxygen has to be reduced. Oxygen must have gained those electrons. So oxygen, O2, let's see, it started with a charge of 0 as neutral, and then I produced here CaO, and that has now a charge of minus 2. So because in calcium oxide, oxygen has that minus 2 charge, it gained more negative charge, it gained those electrons, so oxygen gains electrons, so that must be reduction. Okay. For right now, in terms of a redox reaction, that's really the only thing that I'm going to ask you about. I'll give you a reaction, and I will ask you to tell me what's being oxidized, what's being reduced. We're going to get way more into redox reactions in a different chapter. Right now, we just want to introduce the term oxidation and reduction. I want you to be able to pick out right now what's being oxidized, what's being reduced, and then Also, we're going to talk about oxidation number. So I want you to be able to determine the oxidation number in compounds or of elements. So let's talk about oxidation number then. To determine if an oxidation reduction reaction has occurred, we assign oxidation numbers, or otherwise called oxidation states. It does not matter which one you use, you'll hear them interchangeably. We assign oxidation numbers or oxidation states to each element in a neutral compound or a charged entity. And of course there are rules for these. You will have to know these rules. Once we use them though so many times, it'll be a breeze, you'll just fly through them. So let's talk about the rules. Okay, elements in their elemental form have an oxidation number of 0. What on earth does that mean? That means sodium, chlorine, fluorine, strontium, iron, all of those are just elements. They're in their elemental form. That means they're neutral. Charge of 0, charge of 0, charge of 0, charge of 0, charge of 0. So if I see any element just all by itself and I don't see a charge that's associated with it, like in the corner here, then that means it just is 0. Its oxidation number is 0. Now, what happens if I had a diatomic? Cl2, F2, I2. Any diatomic element is also considered an oxidation state of 0. So any element by itself, any diatomic element, oxidation state of 0. Okay? Next one. The oxidation number of a monatomic ion is just going to be the same as its charge. So if I had Fe3+, the charge of iron is also its oxidation number. So if iron has a 3+ charge here, because it's just all by itself, it's a monatomic ion, its oxidation number is just +3. If it's an alkali earth metal, if it's an alkaline metal, it's in that first group. So it's lithium, potassium, rubidium, sodium, francium, cesium, any of those, they will always have a +1 oxidation number. Always. Doesn't matter what it's bonded with. Alkali metals always have a +1 oxidation number. Alkaline earth metals will always have a +2 oxidation number. And then aluminum will always be a +3. So oxidation number of alkali metals, always +1. Alkaline earth metals, always a +2. So calcium always has a +2 oxidation state. Strontium always has a +2 oxidation state. And now aluminum always has a +3 oxidation state. Okay, so let's go to the next rule. Nonmetals tend to have negative oxidation numbers, although we can sometimes see that in some compounds they will be positive. So if you see that a nonmetal can have a positive oxidation number. So don't freak out. Most nonmetals though do have negative oxidation numbers, but if it's positive, again, that's totally okay. It happens. Oxygen is usually a -2. Oxygen will typically always have an oxidation number of -2, unless it's in a peroxide, which then it has an oxidation number of -1. Okay, so oxygen is always -2 unless it's with unless it's in a peroxide, which would then mean that it would have an oxidation number of -1. So let's look at the difference here. Actually, let's just go on a new one. Okay, let's say I have Na2O2, and then I have O3. Okay, I have sodium and I have oxygen here. This is sodium peroxide. I know that this is sodium peroxide because this has a 2 here and this has a 2 here. I get this 2 coming here because of the charge of oxygen we said is a -2. But this 2 from here would indicate that sodium had a charge of +2. But we know that sodium always has a charge of what? Sodium always has a charge of +1. Always. There's no exceptions to this. Oxygen, though, does have an exception, and that's when it's in a peroxide. So if sodium has a +1 charge here, I need to find the oxidation state then of oxygen in sodium peroxide. Well, I have 2 sodiums, so that means overall I have a +2 charge here for sodium. Oxygen, I have 2 of them, so 2 of them times the oxidation state of oxygen here is going to have to balance out that +2 to give me that overall net charge of 0. So if this is a +2, my goal here is to get -2 so I can balance it out to get a neutral compound. So that means this has to be a -1. So peroxides, always that -1 oxidation state. So this is a peroxide. In this case, I have iron is reacting here with oxygen. Well, iron is a transition metal, and iron doesn't have a specific rule that goes along with it so far that I know. So because iron could be any charge, I'm going to assume then that oxygen must have had this -2 oxidation state. You can see that here too. So oxygen I can say has a -2 because I don't have a rule for iron. But I know then that oxygen is usually that -2 charge. So that's the assumption that we're going to go under. If oxygen is paired with something that I know a rule for, like sodium, sodium's always a +1, then I'm going to start with my sodium first. But if oxygen is paired with something that I don't have a specific rule for with no exceptions, then I'm going to start with oxygen being that -2. So oxygen has a -2 oxidation state, and I see that I have 3 of them. So overall that gives me a -6 charge. So I have 2 iron, so the oxidation state of iron times 2 plus a -6 is going to give me 0. So I need this to be +6 here for this to be -6 to be 0. So something times 2 is going to give me a +6. It's going to be a +3. So that means oxygen is going to have a -2 oxidation state. Iron is going to have a +3 oxidation state. Okay, so hydrogen is typically a +1 oxidation state unless it's bonded to a metal. So hydrogen is a -1 when it's bonded to a metal, but then any other time it's going to be a +1 because it's usually bonded to a non-metal. So if we had sodium hydride, sodium's always a +1. And because sodium's a +1, hydrogen in this case has to be a -1. But in the example of NH3, nitrogen is a -3, so hydrogen must be a +1. Okay, fluorine will always have an oxidation number of -1. The other halogens usually have an oxidation number of -1, but if we see them in oxyanions or polyatomic ions, they can sometimes have positive oxidation numbers. So usually those halogens are sometimes like left for last when we're thinking about a polyatomic. We'll do an example of that in just a second. In terms of oxidation numbers, the sum of the oxidation numbers in a neutral compound is 0. I always want to make my compound overall's charge 0 because compounds are neutral. The sum of the oxidation numbers in a polyatomic ion should be the charge on that ion. So we'll do an example with that as well. So let's just go ahead and do some examples now. Okay, let's say for example, I want to do H2S, let's do S8, let's do SCl2, and let's add a polyatomic in there, Na2SO3. I don't know why I'm digging the sulfur right now. And then let's do SO4 2-. Okay, I want us to find the oxidation number in all of these for each element in all of these compounds. So I have H2S. I do not have a specific rule for sulfur, but I do have an oxidation rule for hydrogen. And that is, if hydrogen is bonded to a metal, it's considered to be a -1 oxidation state. If hydrogen is bonded to a nonmetal, in this case it's bonded to sulfur, a nonmetal, then it's considered to be a +1 oxidation state. So hydrogen should be +1. That's the oxidation number for hydrogen in this case. Well, I have 2 of them. So I have 2 +1s, so +2. So the charge, our oxidation state of sulfur plus +2 is going to have to give me that 0. It's going to have to be neutral because this is a neutral compound. So sulfur then must have an oxidation state of -2. So I have +1 oxidation state for hydrogen, -2 oxidation state for sulfur. Okay, let's go to S8. S8. This is an elemental form of sulfur. So I don't see a charge associated with it, so it's not an ion, it's just an element. So according to my rule, its oxidation state is 0. Okay, let's look at sulfur dichloride. So I have SCl2. In SCl2, I don't have, again, a rule for sulfur. So I'm going to have to go off my rule for chlorine. And we know that halogens, chlorine is a halogen, usually have an oxidation number of -1 unless they're with an oxy anion. So if they're in some type of polyatomic that has an oxygen attached to it. This does not. It's just a halogen, just chlorine attached to a sulfur. So chlorine must have a -1 oxidation state. I have 2 of them. So overall that's -2. So sulfur's charge, or sulfur's oxidation number, plus this -2 has to equal 0, because it's a neutral compound. So that means sulfur has to be a +2. So I have +2 oxidation state for sulfur. Chlorine would be that -1. Let's now go to sodium sulfite. Okay, when I see any type of ionic compound that has that polyatomic, I think about these being separate. So I have my sodium, and then I have my sulfite ion. I think that it breaks it up and helps quite a bit. So I know that sodium is an alkali metal, always has a +1 oxidation number. So I know that one for sure. Sulfite, SO3, overall has a -2 charge. Well, I know that oxygen, when it's not in a peroxide, which this is not, always has an oxidation number of -2. Well, I have 3 of them. So overall, it's like it has a -6 charge. So the charge, or oxidation number of sulfur, plus that -6, has to equal the overall charge on that polyatomic ion, which is a -2 here. So something plus -6 equals -2. So that has to be then +4. So +4 plus a -6 is a -2. So that means sulfur must have a +4 oxidation number. Oxygen has a -2. Sodium has a +1. Lastly, I have my sulfate ion here, SO4-2. So again, we kind of just did this on the last one, but let's just do it again. So oxygen, -2, because this is not a peroxide. Overall, it's carrying a -8 charge. So the oxidation number of sulfur plus a -8 has to equal this leftover charge on the ion, which is a -2. So that means in this case, sulfur has to have a +6 oxidation state. So we had sulfur in all of these cases. In this case, it was a +6 oxidation state. In this case, it was +4, +2, 0, In this case, it was a -2. So some of these elements, some of these atoms will not have always the same oxidation number. That's why we have to have these rules, so then that way we can figure out what the oxidation state is for these certain elements when they're mixed with or bonded with something different or in different situations. So hopefully going through those help out a little bit. I am going to post a few more problems for you to do with oxidation numbers on your blog, and I will also post the answer key to them tomorrow. So just if you want more practice, you don't have to do them if you feel like you know how to do these, but you will be tested for your Chapter 4 test on oxidation numbers, okay? So make sure, again, you're pros and you know all of those rules. Okay, so now we're going to shift gears and go into displacement reactions. In a displacement reaction, most displacement reactions are also considered to be redox reactions. In a displacement reaction, what we have learned is that one element is coming in and displacing another element. So we can also think about it as ions are oxidizing an element, and then the ions are going to then be reduced. So in this specific case here, I am reacting hydrochloric acid HCl with magnesium. So I have hydrochloric acid is reacting with magnesium. So here's my hydrochloric acid here. If I were looking at this on the macroscopic scale, this is what I'm seeing. So I have my acid solution, and here's a piece of magnesium ribbon. So that's just magnesium metal. And then I react it. I see this is my reaction happening here. And then I produced magnesium chloride. I'm getting some, I have still my solution here, but then I also see some gas. I see some bubbles that are forming. Those bubbles, that gas is going to be hydrogen, H2. So let me write this bigger actually, because I don't know that we can see that little tiny print down there. Okay, so we had magnesium was reacting with hydrochloric acid, and it produced hydrogen gas and magnesium chloride. And that is not balanced. Okay, now it's balanced. So in this case, in a displacement reaction, we know magnesium kicked out hydrogen and took hydrogen's spot to bond with chlorine. So I got magnesium chloride as my product, and now because hydrogen was kicked out all on its own, I was left over with my hydrogen gas. So that's why I produced that H2, that hydrogen gas. And that's what's happening in displacement reactions. But not all displacement reactions may occur. And we also just said that in displacement reactions, we can also think of them as redox reactions. So let's see specifically why. So in this case, I had my magnesium reacting with hydrochloric acid. Oh my gosh, there's that bug. It's so disgusting. Magnesium reacting with hydrochloric acid to produce magnesium chloride and hydrogen gas. So magnesium, it's in its elemental form. So that gives me my that gives me my oxidation state of 0. Hydrochloric acid, I know that a halogen is a -1 unless it's in that oxy anion. I don't see oxygen present, so this has to be -1. Hydrogen, it's a +1 when it's bonded to a nonmetal. Chlorine is a nonmetal, so hydrogen is a +1. If I found the oxidation numbers of these, magnesium is an alkaline earth metal. It's always a +2. And chlorine is not attached to oxygen here, so it must be a -1. And then H2, hydrogen, is diatomic, and we said that diatomic elements are considered to have a 0 oxidation state. So if I look at this, magnesium went from an oxidation number of 0 to an oxidation number of +2. So it became more positive. If it gained electrons, it would have become more negative. So because it became more positive, it must have lost electrons, meaning then that it was oxidized. So magnesium in this case was oxidized, Now, hydrogen here was a positive 1, but on this side, hydrogen is 0. So while magnesium was oxidized, hydrogen actually became more negative. It went from plus 1 to 0, so that means it must have gained electrons, so hydrogen is what was reduced. And I know that it wasn't chlorine because chlorine was a negative 1 here on the reactant side, and on the product side it was still a negative 1. So because they were both negative 1, chlorine didn't change at all. So magnesium oxidized, hydrogen reduced. So displacement reactions also show redox reactions as well. Okay, in this reaction, we have silver ions are oxidizing copper metal. So I have copper is reacting with silver to produce copper 2 plus and then silver. So in this case, copper was a 0 and then silver had a plus 1 charge. But on the product side, copper now has a positive 2 charge. So copper went from 0 to positive 2, meaning that it lost electrons, it became more positive. So then that means it must have been oxidized. So copper is going through oxidation. Silver is a positive 1 here. On the product side, it was a 0 charge, or has a 0 oxidation state. So it is losing electrons, so it is going through reduction. Okay, if we reversed this reaction actually wouldn't happen. So if I had copper 2 plus with silver that had an oxidation state of 0, this will not occur. But why is that true? We have to use something called the activity series of metals. And this is my activity series of metals. Right now, we don't have to worry about this part of the column. This is what we're going to get to when we get into our chapter on oxidation and reduction reactions. Right now, I just need to look at this list of metals. So, if I look at my activity series, anything that is above what you're looking at can take the place. So lithium can take the place of any of these in a reaction. Potassium could take the place of anything underneath it, but it could never take the place of what's above it. So lithium could take the place of potassium in a reaction. But because lithium is above potassium, potassium could never take the place of lithium in a single displacement reaction or in a displacement reaction. Barium could take the place of calcium or sodium or magnesium, but barium could never take the place of potassium. Barium could never take the place of lithium because these are stronger metals. These will react, these will oxidize more readily than barium would. So let's say we had zinc. Zinc could take the place of iron, but iron couldn't take the place of zinc because zinc is above it on our activity series. So let's do a couple examples with this. Okay, so let's say, for example, we did iron 2 chloride, so FeCl2, and let's react that with magnesium. Okay, so I need to look here to see, can this magnesium metal take the place of iron in this compound? Before I write my products, I have to go to my activity series to determine if magnesium can take the place of iron. Well, magnesium is here, and iron is down below it. So because iron is below magnesium, magnesium can kick iron out, and that reaction will occur. So magnesium is going to kick iron out. So now magnesium is going to bond with chlorine. So I have Mg and Cl. Magnesium has a +2 charge, chlorine has a -1 charge, so that means I get MgCl2 plus what I have left over, which would be iron, so just plus Fe. But let's say that we did that in the opposite way. Let's say that I had magnesium chloride reacting with iron. Would that reaction take place? Iron, I have to figure out if iron can kick out magnesium in this compound. So I'm going to go back to my activity series. Here's iron, here's magnesium. Iron is below magnesium, so iron can't kick out anything above it, and magnesium is above it. So that means this reaction cannot occur. So I'd have to write no reaction in R. Can't happen, because that single replacement activity series tells me that. I can also have single replacement reactions using halogens, using those halides. So it goes the same way, same rule, kind of like your activity series for metals. So we have fluorine, chlorine, bromine, and then iodine. Those are the ones that we typically use. Fluorine could take the place of chlorine, bromine, or iodine. Chlorine could take the place of bromine or iodine, but chlorine could never kick out fluorine in a single replacement reaction or a displacement reaction. Bromine could take the place of iodine, but it can't take the place of chlorine or fluorine. So, same thing that we just did, we can do with halogens. So let's say we had sodium iodide reacting with fluorine. Can fluorine take the place of iodine? Fluorine is up here, iodine is down below it. Fluorine can kick out iodine. So I could get sodium fluoride, which I know Na is a +1 charge, F is a -1 charge, so NaF, plus iodine, and iodine by itself is diatomic, I2. So then I need to balance, 2 and 2, there we go. So that reaction can happen. But if I did the opposite of that, it wouldn't be able to happen. Okay, so we got through our slides that we wanted to get through today. Now, you're going to have some practice with some types of reactions that we talked about yesterday as well as today. Tomorrow, you're going to just work on practicing reactions that we've done so far through this chapter. And then on Thursday, we'll finish up your chapter 4. So if you guys have any questions, email me, post on the blog, let me know. And I will see you guys so soon. It's like less than 2 weeks now. I'm so excited. I hope you guys have a really great day. Bye.